Hello, good afternoon. Last time we have seen the greedy approach. So this was the skeleton of greedy approach, and the problem that we have seen this knapsack problem, and in minimum cost spanning tree side we have seen the two approaches, that is Prim's and Kruskal algorithm, and one shortest path problem that is based on greedy approach and basically known as Dijkstra algorithms. So this was the knapsack problem. Then it was a minimum cost spanning tree, and it is the Prim's algorithm. And then this was the overall strategy of solving any graph for finding the minimum cost spanning tree using Prim's algorithm. First of all, we will start with the minimum cost edge, and then we will connect to this. Okay, and if n vertices are there, then finally we will be computing n minus 1 edges that will be required for representation of minimum cost spanning tree. So this was all about the Kruskal algorithm. Okay, Kruskal algorithm was based on set structure, that performing the union and find operation on the set. Okay, at each and every time we will select the minimum cost edge, and we will select whether the inclusion will cause a cycle formation or not. And if it does not form the cycle, then we will include this in the minimum cost spanning tree. Otherwise, we will discard that particular considered edge. Okay, then finally this was the single source shortest path. The problem was all about this one source vertex is given. We are remaining n minus 1 vertices are there, so we are interested in finding out the shortest path from that source vertex to all the remaining n minus 1 vertices. So this algorithm was based on greedy approach. At some point of time, we select a one vertex, and we will select the reachability of other vertices from this particular selected vertex, and we will check whether the path can be updated or not, depending on the cost of the shortest path. This was an example that we have covered. Now we will see some questions based on this. The first question: let G be a weighted connected undirected graph with the disjoint positive edge weights. Distinct positive age weight means each and every age is having different weights. Okay, so it is not like that two ages sharing the same weights. And if every age weight is increased by some weight, like you can consider that any particular graph in which age AB was there earlier, the cost of that AB was 5, and if each and every age weight is increased by some value, like if one age is increased by 2, then all the remaining ages will be increased by 2 also. That's what it is saying, that if every age weight is increased by the same weight, then which of the following statement is true? The second one, minimum spanning tree of G does not change. Okay, so this one should be correct, because the age, if one age is increasing, then other age all are also increasing. Okay, so it doesn't change the minimum cost spanning tree. Second thing, shortest path between any pair of vertices does not change. So this is not true, because we are increasing the weight. So the shortest path between any pair of vertices, see, shortest path will not get changed, but it might be possible that length of the shortest path will get changed. Okay, so here if we consider that shortest path between any pair of vertices does not change, if we consider the cost here, then this is false. It means that only P is correct. Okay, so the correct option here is P. So cost can be updated. So shortest path, the cost of the shortest path between any pair of vertices does not change. So this is false. It will definitely going to change, because we are increasing the weights. Then next one, consider a weighted complete graph G with n vertices v1, v2 up to vn, such that weight of the edge vi vj is equal to twice of I minus j. Here you can consider that what will be the cost of v2 v4. See, v2 and v4 is connected. Okay, so in V2 V4 pair, the value of I is 2 and the value of j is 4. Now what we are saying, this is the weight of this age is 2I minus j. So difference between I minus j, and we will take modulus of this. So difference is 2 and it is multiplied to 2. So here what you can consider that this uh, weight, or you can say the cost of this particular age between V2 V4 is 4. Okay, but if you consider V3 V4, if you consider V3 V4, then I is equal to 3, j is equal to 4. Okay, difference is 1. Okay, so what is the cost between V3 V4? The cost between the age V3 V4 is 2 only. Okay, because this expression is 2 multiplied by 1 in that case. So here you can notice that if you consider any consecutive pair like V1 V2 V2 V3 V3 V4 V4 V5, what is the cost of this? The cost will be 2 only. Okay, and this is the minimum cost. Now listen, how many total vertices are there? Total n vertices are there. Okay, so how many edges will be required for the computation of spanning tree? N minus 1 edges will be required. What is the cost of one edge? The cost of one edge is 2. Okay, and how many total edges are there? N minus 1. So the final answer will be 2 multiplied by n minus 1. That is 2n minus 2. So correct option is option B here, 2n minus 2. See the third one, to implement Dijkstra shortest path algorithm on unweighted graph so that it runs in linear time. See in Dijkstra, if you use the Q data structure, then it might be possible that you can run this unweighted graph in a linear time. So the correct option here is Q, option A. Q data structure is based on first in first out data structure. Okay. The next question is, let G, V, comma E be a weighted undirected graph and T be a minimum spanning tree of G maintaining the adjacency list. Suppose a new weighted edge UV belongs to this U, comma V is added to G. The worst case time complexity of determining if T is still a minimum cost spanning tree of the resultant graph or not. So ultimately what you are doing, you are given a graph, you are also given minimum cost spanning tree, that is your T, and what you are doing, you are increasing or you are adding one edge between which vertices, between U and V. So after addition of this particular edge, what is our task? One task is given to you, that find out whether the T will remain same or not. Okay, so how can you determine whether T will remain or T will remain same or not? Because if we add this particular edge, so it might be possible that minimum cost spanning tree can be changed. So that is our task, to determine whether T has been changed or not. Okay, depending on this, what we will do, we will have to search for each and every vertex. Means what is happening on each and every vertex, like go to this particular vertex and check whether this addition of this UV is affecting to this vertex or not. Okay, so the worst case time complexity of determining T is still an MST of the resultant graph is nothing but order of V. Okay, so this is theta of V. So fourth option 4 is the correct option. One more question. See the graph G, V, comma E, where total 100 vertices are there. Okay, and these are the edges, and Vij is equal to mod of I minus j. Okay, here the similar question that we have seen, that Vi, comma Vj, the weight of this particular edge was 2 multiplied by I minus j, but here it is only I minus j, and we are taking the modulus of this. What is the meaning of this? If we take V2 comma V3, V2 comma V3, okay, then the cost is 1. And if you consider the cost between V2 and V6, okay, so this will be 2 minus 6. Okay, so modulus of this is 4. So the minimum age will be in the consecutive pairs like V2, V3, V3, V4, V4, V5, V5, V6, and so on. So total, how many vertices are there? 100 vertices are there. So how many edges will be there? 99 edges will be there. in the spanning tree. If 99 edges will be there in the spanning tree and cost of one edge is 1, then total, what is the cost of minimum cost spanning tree? 1 multiplied by 99. That is correct option here is 99. See the next question. Consider the following undirected graph G. Okay. Choose a value of x that will maximize the number of minimum weight spanning tree. Okay. So it might be possible that one graph is there and multiple minimum cost spanning tree is possible. Okay. Multiple minimum spanning tree is possible. So when multiple minimum spanning tree is possible, suppose if each and every edge is having distinct weight, in that case, single spanning tree is possible by using any of the approach like Prince or Kruskal. But if you are having multiple edges, like here, what you can see. So if you can use repetition. So see here, this is cost edge 1. Okay. So if we take this x is equal to 1, then we will see if x is set to 1, then total how many spanning trees are possible. So initially we can include this one or this one if you are using Kruskal algorithm or if you are using Prim's algorithm. Okay. So if we consider this as vertex or this edge cost is 1, then for this one corresponding to this particular one, one spanning tree is there, corresponding to this one another spanning tree is there. Okay. If you consider this as 3, okay, so corresponding to this 3 one spanning tree is there and corresponding to this 3 another spanning tree is there. But see, if you take x is equal to 4, if you see x is equal to 4, then how many edges are there which is having weight 4? This is one edge, then another edge, then third edge, and then fourth edge. 4 edges are there which is having weight 4. So here see, if 4 edges are there and each of which is having weight 4, then what you do initially, you will select this edge of cost 1, then next step you will select edge of cost 3. After that you can select this edge of 4 or this edge of 4 or this edge of 4. Depending on this, 3 spanning trees are possible. Okay. So what is the correct value of x for which we maximize the number of spanning tree? That is 4. Okay. Okay, the next question. Consider the weight and values of the item listed below. Note that there is only one unit of each item. Okay. So this is nothing but the fractional knapsack problem. The task is to pick a subset of these items such that the total weight is no more than 11 kg. Okay, so 11 kg is the knapsack capacity, and their total weight is and the total value is maximized. So our aim is to maximize the values. Okay, so this is weight and this is value. Moreover, no item may be split. Okay, see, this is very important. Moreover, no item may be splitted. So what does it mean? If item is not splitted, then it is not a fractional knapsack. It is a binary knapsack problem. Means if you are including this, then you should include it completely. Otherwise, you cannot include this. The total value of the item picked at an optimal algorithm is denoted by VOPT. Greedy algorithm sort the items by their values to weight ratio. So value to weight ratio we will consider. Okay. In the decreasing order of and pack them greedily, starting from the first item in the ordered list. The total value of the item picked by the greedy algorithm is denoted by V greedy. Okay, so what is the value of V optimal minus V greedy? The first thing is that you need to find the value per this. What is that parameter? Value to cost. Okay, so what is the value to cost ratio? What is the value to weight ratio for first item? This is item 1, item 2, item 3, item 4. Okay, this is value, this is weight. Value to weight ratio for first item is 6. 60 multiplied by 60 divided by 10. So this is 6. Value to weight ratio for second item is 4. 7 4 are 24. Value to weight ratio for this third object will be 5. 4 5s are 20. And value to weight for the fourth object is 12. That is maximum. Now, if you are selecting greedy approach and we are selecting this first one, okay, so which object is selected first? The fourth object is selected first because value to weight object for the fourth object is maximum, that is 12. Okay, so you will select the fourth object. What is the value associated with the fourth object? Value associated with the fourth object is 24. Okay, and what is the remaining knapsack capacity? Total capacity is 11. So you utilize this 2 for storing this fourth item. Remaining knapsack capacity is 9. Okay. After that, what is the second item in the value to weight ratio list? This third item will be 5, fourth item will be 4, and this first item will be 6. So what you will consider? We will consider the first item. But here, what is the weight of this first item? 10. And what is the remaining knapsack capacity? 9. So we will not consider this. Okay, then we will consider the next. What is the next one? This is next. Okay, so next one is this third object for which value to weight ratio is 5. Okay, so you will include this. What is the accumulated weight, accumulated value? This is first was 24 and second one is 20. See, after inclusion of this third object, we cannot include any more object. What is the total value? Total value earned is 20 plus 24. That is nothing but 44. 44 is nothing but the value adapted in case of greedy approach. But what should be the optimal value? In optimal case, we want to maximize the profit. See, if instead of considering this object 3 and object 4, if I directly include only single item, that is first item. Okay, what is the weight? Weight is 10. And if I select the first item, then how much profit I earn or how much value is associated with this? It is 60. So that is maximum. That is very large as compared to 44. So that's what it is asking. What is the value? What is the difference between V optimal minus V greedy? So 60 minus 44. What is the result? 60 minus 44 is 16. So correct option here is 16. 1 6. Okay, next paradigm for algorithm design is dynamic programming. Dynamic programming is basically based on two main principles. The first one is overlapping subproblems and second one is optimal substructure. Okay, it is based on principle of optimality. What is principle of optimality? It says that whatever the initial state or decisions are, the remaining decisions or must constitute an optimal sequence, an optimal decision sequence with regard to the first decision. Okay. Just understand this. What is overlapping subproblems? Here you can see if I am computing the Fibonacci of n. Okay, so how the Fibonacci is computed? Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2, where n is greater than 2. But if it is 0 or 1, means if n is equal to 0 or if n is equal to 1, then we will be computing the first and second item. So it will be n only. So what is the Fibonacci series? Initial value is null. Initial value is 0. After that 1, then 0 plus 1 is the computation of third 1. So 1 plus 1 is 2, that is fourth, and so on. Okay, so see, this is the recurrence tree for computing the Fibonacci 7. So Fibonacci 7 is computed. We will consider this if n is greater than 2. So Fibonacci 7 is splitted into two parts, Fibonacci 6 plus Fibonacci 5. Again, Fibonacci 6 is splitted into two parts, Fibonacci 5 plus Fibonacci 4. Here you can see Fibonacci 5 here. Here also it is computed Fibonacci 5 and here also it is computed Fibonacci 5. So it is known as overlapping subproblems. This is same subproblem, Fibonacci 5, Fibonacci 5. So here we are computing once again, and once again this Fibonacci 5 is completed. Instead, what is an idea? If this Fibonacci 5 can be stored somewhere, and later on if we require that what is the value of Fibonacci series or what is the value of Fibonacci 5, in that case we are not going to expand this tree further. We will just refer to that stored value and we will get that value from that particular storage. That is the overall idea behind dynamic programming. So what does it do? It store some computed value in the table, and whenever it is required in the future, then it will collect that value from that table. Okay, so it will not compute again and again the same value. It is known as overlapping subproblem. The second thing is optimal substructure. Optimal substructure is that Suppose take an example. If you are interested in computing the shortest path from A to B, okay, and C is some intermediate vertex on the shortest path. So what does it mean? It is saying that if A to B is the shortest path and C is some intermediate vertex on that path, then A to C and B to C must be the optimal substructure. Okay. So what does it mean? This A to C must be shortest path between this vertex A to vertex C, and if A to C, sorry, and C to B is also the shortest path between this vertex C to vertex B. This is known as optimal substructure. So each and every substructure is an optimal one. The various problems are there that belongs to this category. The first one is suppose matrix chain multiplication, longest common subsequence, optimal binary search tree, single source shortest path. Here also we will see single source shortest path algorithm, the same single source shortest path algorithm that we have seen with the greedy approach. But what is the difference? Some differences are there behind the solving of behind the scenario or behind the approach that is followed in case of greedy approach or in case of dynamic programming approach. Here single source shortest path algorithm take care of negative edge also, and this algorithm is known as Bellman-Ford algorithm. Then a multi-stage graph is there, and all pair shortest path algorithm is there. Okay, so we will see this one. We are not going to cover this completely. We will see two three problems based on this dynamic programming. So first we will see matrix chain multiplication. Now first understand what is matrix chain multiplication. First, what is matrix multiplication? Suppose two matrices are there, matrix A and matrix B. If you want to multiply these two matrix A and B, then what is the condition for multiplication? The number of column in first matrix should be same as the number of rows in second matrix. Suppose the dimension of matrix A is m cross n and dimension of second matrix B is p cross q. So in that case, n is equal to p for the optimal multiplication, and in the resultant total how many entries will be there? Total entry will be m cross q will be entries will be there, and how multiplication is performed? One complete row of the first matrix is get multiplied to the one complete column of the second matrix. Then you compute the single entry of the resultant matrix. Okay. What does it mean? In other words, we can say that n n is what? N is nothing but the number of columns in first matrix. And what is p? P is nothing but number of rows in second matrix. So n is equal to p. So n or p, these many multiplications are required for the computation of one entry in the resultant matrix. And total how many such entries are there in the resultant matrix? Total m cross q entries are there in the resultant matrix. Now, total number of scalar multiplication for the entire multiplication of A multiplied by B is equal to m cross n cross q, or m cross p cross q, because n and p is same. Now, what we are interested in, here we have given the sequence of matrices, matrix M1, M2, M3, M4, and so on. And each sequence is compatible of multiplication. Like, what does it mean? M1, M2 can be multiplied, M2, M3 can be multiplied, M3, M4 can be multiplied, and so on. What we are interested in, we are interested in finding the shortest, in finding the optimal sequence for multiplication of these matrices such that the total number of scalar multiplication would be minimum. Here, we are not actually multiplying. We are just computing the optimal sequence of multiplication, so that if we perform multiplication in that sequence, then we are having minimum number of scalar multiplication, because multiplication is a very costly operation, and here the fundamental operation here is multiplication. So basically, we are interested in minimizing the number of scalar multiplication with the help of this dynamic programming approach. Here you can notice that this Mij is a recurrence relation. Mij is nothing but minimum number of scalar multiplication for performing the actual multiplication from matrix I to matrix J. Okay. Here we will check this. We will find this K, where K is ranging from I to J minus 1. Here you can notice that I is less than or equal to K less than J. So first one is Mik, second one is K plus 1 J, and This is nothing but performing multiplication of first part, performing multiplication of second part, then one result is generated from first part, another result is generated from the second part. Now these two results will be multiplied, and while multiplying these two results, these many multiplications are more required, pi minus 1, pk, pj. Okay, and this is when I is less than j, and if I is equal to j, it means that from matrix I to matrix I, from matrix I to matrix I, no multiplication is required, because only single matrix is considered in the sequence. Now ultimately, first see the example here. So these are six matrices: a1, a2, a3, a4, a5, and a6. The dimension of this 30 cross 35, 35 cross 15, 15 cross 5, 5 cross 10, 10 cross 20, 20 cross 25. So here we can see phase 1, phase 2, phase 3, phase 4, and phase 5. So initially, this is the initialization. Mij, sorry, Mii is equal to 0. Means M11 0, M22 0, M33 up to M66 is 0. Okay. Now, in phase 1, we will be computing M12, M23, M34, M45, M56. What does it mean? Here you can notice that this horizontal is indicated by variable I, this vertical is indicated by variable j. Okay. Here, if I am interested in writing Mij, so what is the value of I for this column? The value of I for this column is 1. What is the value of j? 1, 2. So see, if I compute M12, so how many matrix will be considered? Only two matrix will be considered, M1 and M2. What is the options? Only one option is there, just directly multiply this. Okay. So if you multiply these two matrix, then how many multiplications are required? So what is the range for this k? Range of this k will be from I to I only, because this is from I to I plus 1, and if it is from I to I plus 1, then the value of k will be I. So here what we will write, this is Mii, this is Mjj, and it is Pi minus 1 Pk multiplied by Pj. So this one will be P0, P1, and P2. What does it mean? If I perform this multiplication A1, A2, okay, so this is my m cross n, and this is my p cross q. N is equal to p. What is the resultant size? The resultant size will be 30 cross 15. 30 cross 15 is the resultant size, and how many multiplications are required for the computation of one element of the resultant? 35. Okay, so here total number of multiplication will be 30 multiplied by 35 multiplied by 15. So this is 15,750. Okay. Then M23. Here I is equal to 2, J is equal to 3. M23. 35 multiplied by 15 multiplied by 5. Then you will get 2625. Similarly, you will compute M34. M34 is this 15, 5, 10. 15, 5, 10 is 750. After that, M4, 5, 5, 10, 20. So this is 1000 and so on. Here, this is known as phase 1. After phase 1, we will be computing phase 2. Now in phase 2, what is the value of I? I is 1 and j is 3. Here, what is the value of I? I is 2, j is 4. So what we are computing? We are computing 1, 3, M1, 3, M2, 4, M3, 5, M4, 6. What does it mean, or what is the difference between the computations performed in phase 1 and phase 2? In the computation performed in phase 1, the difference between I and j was set to 1. Here, what we are computing? We were computing M12, M23, M34. The difference between I and j is 1. But in phase 2, what we are computing? We are computing M13, M24, M35, and so on. In phase 3, this difference is once again increased by 1. In this, we will be computing M14. Here you can see phase 3. We will be computing M14, then 25, then 36. In fourth phase, we will be computing 15. Difference is 4, 26. And in last phase, we will be computing M16. 16 is the final entry that we are interested in. What this 16 indicate? 16 indicate the minimum number of scalar multiplication for the actual multiplication from matrix 1 to matrix 6. See the algorithm. n is equal to length of p minus 1. First of all, we will compute what how many matrices are given. Then this second line, it is running from 1 to n. Mi is set to 1 means m11 initialized to 0, 22 is initialized to 0, 33 is initialized to 0, and so on. Now here, this is the main construct. Here you can notice that total how many for loops are there? 3 for loops are there. This is outermost, this is middle, and this is the innermost. Outer for loop indicate the phases: phase 1, phase 2, phase 3, phase 4, phase 5. Here you can notice that total how many matrices are there? Here in this example, total 6 matrices are there. If 6 matrices are there, then how many phases will be there? Phases will be 2 to n, and 2 to n means how many times? 2 to n means n minus 1 times. What is the value of n in this example? The value of n here is 6, and n minus 1 is 5. So here you can notice that 5 phases are there. So what does it mean? When r is equal to 2, we will be computing the first phase. When r is equal to 3, then the second phase. When r is equal to 4, then third phase, and so on. Now, when you come to this first phase, then we will be deciding I and j. Okay. For this first phase, what is the value of I? Here, I is 1. Here, I is 2. Here, I is 3. Here, I is 4. In the second phase, I is once again starting from 1, then starting from 2, then 3, then 4. Then in third phase, once again, I is starting from 1. What does it mean? In each and every phase, I will be starting from 1. Here you can notice that this I will be starting from 1. See the end of this I. Here, the last value of I is phase 1. Last value of I is 5. Phase 2. Last value of I is 4. Phase 3. Last value of I is 3. So, last value of I is getting decreased. See the algorithm. This is running from n minus r plus 1. What is r? R is nothing but the outer loop. So here, when the value of n is equal to 6, so it will be 6 minus 2 plus 1. So it is 6 minus 1. 6 minus 1 is 5. Here you can notice that I is ranging from 1 to 5. In the second phase, it will be ranging from 1 to 4. In the third phase, it will be ranging from 1 to 3, and so on. Okay. Depending on this I, we will be deciding j. What does it mean? See, if you are in phase 1, if you are in phase 1 and I is equal to 1, then j is equal to 2. When I is equal to this, I is incremented, then j become 3, then j become 4, and so on. Okay, means the difference between I and j is 1. In the next phase, this difference is increased by 1. In the next phase, this difference is again increased by 1. Okay, so depending on that, we will have to decide the value of j. So see here, j is a function of r and I, and how it can be computed? So just consider this I plus r. What do you mean by I plus r? R is starting from 2, I is starting from 1, so r plus 1 is 3. So but here, when I is equal to 1, j should be 2 only. So here I plus r minus 1, so j is 2. And after deciding I and j, you need to find out the value of k. Means here, when you have decided I to j, then we are interested in finding out the value of k. What is the range for this? Range for this is I to j minus 1. So here you can notice that k loop is running from I to j minus 1. Okay, what you are computing? You are computing q is equal to mk plus 1 j pi minus 1 pj. This is nothing but that recurrence equation. Okay, and if q is found to be smaller than mij, then we will just choose the minimum. So mij is equal to this q, and sij is equal to k. What this sij is stored? Sij is storing the value of that k for which this entire expression is getting minimized. Okay, and similarly, when after computing this m and s, m is the matrix which is storing the minimum number of scalar multiplication, and s is storing the value of k for which it is getting minimized. This is the result for printing the matrix multiplication sequence. This is just an example. If I am computing m25, So I is equal to 2, j is equal to 5. Okay. What is the range for k? Range for k will be 2 to 4. Here you can notice that this one will be M22. Then it is actually MIK plus MK plus 1 J. So this is when the value of k is equal to 2. Here k is equal to 2, here k is equal to 3, here k is equal to 4. If it is from 2 to 5, then the value of k will be 2, 3, 4. So here first value is 2, then second value is 3, then third value is 4. If it is k, then it is starting from k plus 1. So 2, then it is starting from 3. Then if it is 3, then it is starting from 4. If it is 4, then it is starting from 5. Okay. And here you can notice here this is pi minus 1, pk and pj. So if it is 2, then it is P1. Okay, what is the value of J? J is fixed, 5. So P1, PJ, this is fine. P1, PJ, this is fine. And P1, PJ, this is fine. What is the middle term? Middle term is PK. Okay, so here K is equal to 2, that's why it is 2, P2. Then this is P3, then this is P4. For which we will be computing this, and for which it is minimized. We will be storing that value of K in variable S. So similarly, this is one computation 7125 that you can also see here 7125. Finally, this is 15,125 is the minimum number of scalar multiplication required for the actual multiplication from matrix 1 to matrix 6. These are the computational matrix that we are storing, that we are computing in the due course of the computation. So here you can notice that this is I and this is J. This is the M computation, and this is the S computation for which it is getting minimized. Okay. So here you can notice that if we see this, total 5 elements are there. The difference between here is 2. Okay. So this I is equal to 1 and J is equal to 2. This is M12. Here I is equal to 2, j is equal to 3, M23, M34, M45, and 56. Okay. After that, we will move to the next row. Then it is M13, 24, 35, and so on. The difference is 2. Okay. Similarly, you will be storing the value of k here. Now see here, how many matrices are given? 6 matrices are given. What is the value of S for M16? The value of S for M16 is 3. What does it mean? First 3 elements or first three matrix will be multiplied first, like M1 to M3, and in the second pair it will be M4 to M6. Now see, when you come to this first option, in which we are multiplying these first 3 matrices M1, M2, M3. Now I am interested, how many options are possible? We can multiply M1, M2 first and the result is multiplied by M3, or we can multiply M2, M3 first and M1 is multiplied to the result of this M2, M3. Now, for this, we need to identify or we need to see S13. Now, just see what is the value of S13. This is the value of I1 and this is 3. So, here you can see S13 is 1. It means that M1 is considered and M23 is multiplied first. M23 is multiplied, M23 is multiplied first, and M1 is multiplied to the result of M23 later on. Okay. In the second part, we will be having M4, M5, M6. Once again, two are there. M4, M5 can be multiplied, and this result is multiplied to M6, or M5 or M5, M6 is getting multiplied, and then M4 is multiplied to this result. For which we need to see S46. Now see what is the value of S46. What is the value of I is equal to 4 here? This is 4. Okay. Now we will have to see S46. So this is 6. Now see S46 is 5. It means that M4, M5 is multiplied first and later on it is multiplied with M6. Okay. Depending on this S, we can find the actual sequence. Okay, one more thing that is remaining, the time complexity of this. See, this outer for loop is running n times. This inner for loop is running approximately n times, as it is a function of n and r. This innermost loop is running I to j minus 1. It means that j minus I times. And more specifically, we can say that I and j are the upper bound of I and j is n only. So more generally, we can say that it is running n times. This middle loop is running n times, and the last loop is also running n times. So the total time complexity of this construct is order of n cube. So final time complexity of matrix chain multiplication is order of n cube. Okay, the second problem that we will see is the longest common subsequence, in which what does it mean longest common subsequence? So two sequences are given, and we are interested in finding out